This is the module on parent graphs and transformations. We'll be looking at different types of graphs and how they relate to the basic model of the graph and how they have a vertical shift and horizontal shift and all of the aspects, the changes that can go on with a basic model versus a model that's given as a function. I like to say basic model because when you're talking about a vehicle, you go buy a new vehicle, you can buy the basic model, which just has a radio and a maybe air conditioning, and then you have the power windows, power doors, power door locks, power seats, and then you have another model that has heated seats and has dual climate control and all the DVD players and all that. So everything stems from the basic model of the car, except it's just got more bells and whistles on it. And with these models, these are the basic models. These are the models that are around the origin, and all the vertical shifts and horizontal shifts and compressions and stretching is going to take place from these basic models. So you have the linear function, which is f of x is equal to x. You have the nonlinear function, which we'll be dealing with a good bit in the college algebra kickstart, and those are parabolas, and they're parabolic functions. And you have the x to the third power. And when we're talking about x to the third power, I might as well go ahead and say x to the fifth and x to the seventh. Anything to the odd power is going to have a shape like the third power. The only difference is the higher the power, the more that this right here is going to be flattened like that. Okay, so I don't know what's going on. Sorry, I don't know what just went on with my, there we go. Okay, so anytime you have a odd power, you're going to be having this type of function. And the higher the power, the higher the odd power, the more of a flattening effect you're going to have right in here. Like that. Over here you've got your x to the fourth, and this is the even powers. So you might want to put a note under this one. These are your odd powers, and these are your even powers. Your ending behavior is going to be the same. It's going to be the same with the flattening going about the origin, and the ending behavior is going to be both on the odd, it's going to be opposite directions, where the even is going to be the same direction. Absolute value is right in here, and the absolute value, just remember value starts with a V. It looks like a V. The f of x is equal to the square root of x. I kind of call it a swoosh because it looks like it's a swoosh going to the right. And then f of x is equal to 1 over x. Looks like a half a volcano. And if you look at f of x is equal to 1 over x squared, then you've got a full volcano. So that's how I come up with half a volcano, because the x squared looks like a full volcano. And that's the parent graph. So everything we're going to be talking about with transformations, with vertical shifts and horizontal shifts, are going to be coming from these basic models. So if we say it's got a vertical shift of 3 and a horizontal shift of 2, and the orientation is wider, then that is a basic model, but it has bells and whistles on it. And the basic model is these models right here. It'll make more sense as we go through some more examples. Let's take a graph and let's just graph something simple like y is equal to x squared. And this is the basic model that I showed you on the previous, this is the nonlinear parabola, the second one on the top. And it's going to look just like that. So there's our function, and we put our x and our y coordinates, and there they are. And then we plot our points and plot those points as we have them over here. And there is our basic model. Looks like a parabola, and it keeps on going. I just to show you the shape. All right, now let's see what happens when we put a 2 in front of it, and that's a. Y is equal to ax squared. Okay, and I'm just going to put that right over here. I'm going to say y is equal to ax squared. We're looking at what a tells us. What does that coefficient tell us when we're looking at a function? And that's what we're trying to learn here. This first section, we're trying to learn what the equation tells us, or the function tells us, without even doing any math. And by the time we get through with this module, you'll be able to tell, without even doing the plotted points or anything, you'll be able to tell what the function is telling you. So we put our x and our y, and we got some points there. We plot those points. And what you're going to see, I didn't have an 8, so I put it as high as I could go. And there's that point, and there's that point, there's that point, and there's that point. And our graph looks like that. Now, as you can tell, when a is greater than 1, the function is compressed. Okay, compressed along the x-axis. So it's kind of like a vise. It's kind of like a vise going in that way and in that way. And it's being compressed along the x-axis. But it's being stretched along the y-axis. So it's like a rubber band. If you was to take and go along the y-axis and pull up along the y-axis, it would stretch. Okay, but if you was to go along the x-axis, it would be compressed. So this one is being compressed along the x-axis and being stretched along the y-axis. Okay, so that's when a is greater than 1. Well, what's next? What if a is between 0 and 1, like a fraction, a proper fraction? Then we pick multiples of the denominator, so we don't have to worry about fractions. And we pick -4, -2, 0, 2, and 4. And we get a function that looks like this. And if you notice, with the y is equal to 1/2, we're starting to see a wider function. Okay? Because a is between 0 and 1, meaning a proper fraction. And if it's a proper fraction, it's going to be stretched along the x-axis, and it's going to be compressed along the y-axis. Okay? So in this one, you could say it's wider, but you need to say that it's compressed along the y-axis, and it's stretched along the x-axis. So just think of you putting your thumb and index finger on one side and your thumb and index finger on the other and pulling along the x-axis. That's stretching it. But if you was to put your left hand on the bottom of the function and your right hand on the top of the function and squeeze it, it's being compressed along the y-axis. Okay? So if a is between 0 and 1, it's wider. If it's above 1, it's going to be thinner. And that means it's going to be stretched along the y-axis, and it's going to be compressed along the x-axis. So that's kind of like the vise. I call this one the vise because you're used to seeing that with a vise, with something compressing like a balloon. Think of a balloon. If you take up a balloon and you fill it full of air and you push it, then it's going to elongate. It's going to get thinner. But if you take and pinch the two sides and pull it, it's going to get wider. And that's what's happening with the last two problems. But what if you was to have a negative in front of A, meaning A is less than 0, if meaning a negative. So go ahead and put a negative there so you know what that means. If A is negative, that means it's going to be doing the opposite. So there's your points. So if A is negative, it's going to be going in the opposite direction. Okay? So we know that this is the basic model, and everything is compared to the basic. So that's the black. If you can tell on your screen, that's the black. Okay, everything is happening compared to that black line. That's the basic model vehicle. And then everything else, one's got power windows, one's got power doors, one got heated seats. All of them are different, but they're compared to that black parabola. Okay? So the only thing about A is less than 0, you got to remember, it's the same parabola as f of x is equal to 2x squared. Only it's going in the opposite direction. And when a parabola opens downward, that's what you say. This one is opening downward. You don't say pointing downward, you say opening downward. And all these are opening upward. Okay? So A, which is in front, the coefficient in front of the x squared function, it tells us the orientation, the compression, the stretching of the function. Now, what about the horizontal shift and the vertical shift? Well, let's go back to our x squared function. That's our basic function. And if you look at this x squared function, you'll see that the -4, you see that it is not attached to the x, it's attached to the actual function. And you'll see that in just a minute when I go over horizontal shift. You'll see the difference. Now, when a number is attached to the function, that's the vertical shift. And we plug in our numbers. And I plugged in a few extra numbers because that -4 is going to move it a little bit. So that's why I had to put in some extra numbers. And there's our points. And there's our parabola. And let's compare it to our basic parabola. Now, it looks like it's not the same, but if you take the basic parabola and if you move it, then you'll see that it is the same parabola. If you was to move that down, it would be the same parabola. And you see that the difference between the basic model and the one we're buying, or the one we're thinking about buying, is that it has something more than just the basic model. It has a -4 shift, which means a vertical shift down. So the origin now in the basic model is 0, 0. But the origin on the newer model, or the newer function, is 0, -4. So we can say that anytime a number is outside the function, that's going to be our vertical shift. And it represents that area right there. Okay. What about if we do the following? Have a 2, and we have that 2 right there with the x. Now when the 2 or when a number is attached to the x inside the function, see, here's the function. The function has the parentheses around it. If you notice, the function has the parentheses around it, and those parentheses are together. So that means that you have a horizontal shift. And there's your points, and evidently they were already on the oh, I know, I had to double them, make them show up better with the turquoise color. There we go. There's your function. And if you'll look, there's the basic function. We're comparing it to the basic function. And what kind of horizontal shift do you think we'll have? Well, it's going 2 to the left. Now, the first thing you're going to say is, well, that says positive 2. Well, yeah, when you have a times x minus h, that is the original form plus k. That's the original form. Now, if this is to be correct, then I would have to write it a times x minus a negative 2 plus k, sorry. And that is x plus 2. So either I can explain it like this, or I can just tell you to take the opposite. Okay, so if it's a positive 2, that means it's going to move left 2. If it's a negative 2, that means it's going to move right 2. Or you can plug it through the original form and then manipulate it to where you'll see that it is a negative shift. Okay, now what does the 4 tell us again? The 4 is k, and that's the vertical shift. So we notice the 4 is outside just like last time. So that's the vertical shift. But this time, let me erase my, sorry about that. This time we have a h, and that h is a positive 2. And that means that it is a horizontal shift. And I also put the note there. The horizontal shift is always the opposite direction due to the x minus h property. There you go. And the 4, there's the 4, and there's the vertical shift. What have we learned? In this section, in this module, we have learned that the basic form of a quadratic equation, or the intercept form, I'm sorry, is f of x is equal to a times x plus h quantity squared plus k. Now, you're used to a quadratic equation looking like this. 0 is equal to ax squared. Oops, hold on. Let me erase that. 0 is equal to ax squared plus bx plus c. Well, we're going to manipulate this using completing the square in the next section, next unit. I mean, in college algebra, we're going to use completing the square to go from here to there. And then that's going to give us a times x plus h quantity squared plus k. The a, what does a tell us? A tells us what it looks like. Is it going to be wide? Is it going to be skinny? Is it going to be opening downward? Is it going to be opening upward? That's what A tells us. And the A will always be in front of the parentheses. If it's not there, if there's nothing there, it's 1, which means it's a basic model. H is the horizontal shift. And the biggest thing you have to remember about the horizontal shift is that since the property is x minus h, it's always going to be the opposite direction. Okay, it's always going to be the opposite. And the k is the vertical shift. H and k both give us the vertex. Okay, if you look back here, oops, the vertex is this guy right here, the point. That's the vertex. Okay, and there's 2 ways to write your final product when we're doing completing the square. This is the intercept form, and this is just the basic form that you get when you finish the completing the square. Now, I tell students that when you get this, it's going to be the opposite of both, and when you get this, it's going to be the opposite of this, and you just bring this down. But we'll get into that later with completing the square. Now, what about if we have the absolute value? Well, same rules apply. Here's the basic model. So look at this function. Look at this function right here and tell me what you think would happen with this function right here based on what we learned. Well, 2 means it's going to be skinny. It's going to be compressed along the x-axis and stretched along the y-axis, so it's going to be skinny. Positive 3 means it's going to be 3 to the left, and negative 4 means it's going to be 4 down. And that's what it means. There's the 3 to the left, and there's the 4 down, and it's going to be skinny. And that's what it looks like. And the compression is along the x-axis. And if you was, you can either say it's being compressed along the x-axis or it's being stretched like a rubber band along the y-axis. Okay. What about another one? Here is an x cubed function. So look back at your parent graphs, and you know that the cube function looks like a kind of a S-looking thing, curve. Well, same thing. 2 means it's going to be compressed along the x-axis like a vise, like a balloon, and it's going to be stretched along the y-axis like a rubber band. So it's going to have a horizontal shift of 3 to the left and 4 down, just like the other ones. There's the basic model. There's our vertex. And there's the 3 to the left. And there's the 4 down. And there is our function. And notice that it is a little bit stretchier. It's stretched a little bit, so it's more elongated than the basic model. I hope that helps.